Good afternoon. We're very fortunate today to have as our distinguished speaker, Dr. Tom Koch, who is the Dean of the College of Optical Sciences at the University of Arizona. For those of you who don't know, it's very unusual to have an entire college focused on optics and photonics, and at University of Arizona, it's one of only a handful, I think 3 or 4. Right? It formerly was the Optical Science Center, a long-time leading research center for optics and photonics. Tom is one of the foremost experts in, as you can see, in Photonic Integrated Circuits, or PICs for short. For those of you who've never heard of PICs, think integrated circuit, but instead of electrons and microwaves on wires, we have photons and optical waves in waveguides or other structures. Tom's career is an interesting blend of industrial and academic experience. After his degrees at Princeton and Caltech, he spent the first part of his career at Bell Labs. He was a leading researcher in lasers and other communications devices there. He then went into industry for a couple of years, returned to Bell Labs and Lucent as a chief technology officer for optoelectronic products, and eventually moved out to a spin-out company that was spun out of Bell Labs called Agere. About a decade ago, he joined our ranks and he became an academic at Lehigh University as a chair professor in their electrical computer engineering department, and then the center director for their Optical Technology Center. And most recently, just a year ago, he became dean of the Optical Science Center, or College of Optical Sciences more properly. He's received numerous accolades and awards. He's a Fellow of IEEE, Optical Society, a member of the National Academy of Engineers. The Photonic Society awarded him the Streifer Award for scientific achievement, and he's also a winner of the IEEE Sumner Award. He has a great reputation as a leader and mentor over the years, and I can attest to this personally. I've known Tom for, I just did the math, about 30 years. His last year as a grad student at Caltech was my first year. So we didn't know each other very well, but we did meet. In fact, we met in a very fortuitous way for me. I was a new student trying to get some work going in the lab, and my professor was also very new, and we had very limited equipment in the lab. In fact, we were outfitting the labs as I started. And I was trying to get a particular experiment going to characterize laser diodes, their coherence properties. And I built an interferometer, but I needed a micro-positioner, piezoelectric translator, in fact. And I didn't have one, and I really didn't want to wait to order one. So I don't know whether it was in the corridor in the lab. I ran into Tom and told him about my dilemma, and he said, "I think I have one." And he took me into his lab, and I remember you opening a drawer, and there it was exactly what I needed. And so it really helped me, in fact, contributed to my first publication. So I was very happy with that. But he admonished me a little bit. He says, "I'm going to loan this to you, but don't tell the professors I did this." So I didn't really understand what that meant, but now maybe it's out. The word is out. So anyway, please help me with a warm welcome for Tom Koch.
Thank you, Mike. Let's see, is this microphone? I guess it is going. Very good. Well, thanks, Mike, and I want to thank Len for inviting me. I was happy to spend the day with meeting a bunch of colleagues that I've known over the years and getting a glimpse. This was my first visit to the University of Delaware, so getting a glimpse, short glimpse anyway, firsthand of all the great things you guys have going on here. So very impressive operation, and you've got a great team of faculty and some great students that I met today, too. Once I heard you were going to tell a story, I got a little worried, but that story's okay, so that's good. So I'm going to give you a little talk here on photonic integration. First, I'm going to tell you a little bit about Arizona, because if I'm coming here as an ambassador from Arizona, I thought I should say a few words about the College of Optical Sciences. And Mike pointed out I'm brand new there, so when I went to Arizona, this is what I had in mind. You know, I was going to be on golf courses and seeing cactuses and beautiful geography and so forth. And instead, this is what I got. This picture is taken from my bed, literally, looking out my bedroom window. So it's kind of an adventure out there. We get wild pigs They come in herds of 20 at a time, and you can't really see it there, but they're very dangerous. They have tusks, and they'll take out your dog if your dog gets to them before you do. But then we have wild tortoises and Gila monsters, all kinds of exciting things. So maybe this is what you should think of when you think of Arizona. It's pretty wild and woolly place. But in actuality, you should think of the University of Arizona and Tucson. And just to give you a profile how we are compared to Delaware, we're probably roughly twice the size in terms of number of students, and a significant research profile also. We were very highly ranked in physical sciences and funding from the National Science Foundation, and a lot of that is because we have an appetite for doing what we would call big science. We'll get involved with asteroid landing missions where we'll, $1 billion mission where we'll go out and orbit around an asteroid and land on it and pick up a sample and bring it back to Earth, and it's actually orchestrated by the university. So these are big projects and big telescope projects that I don't have time to go into. But if you look at the campus, you can see the mountains. I actually live way out by this mountain. That's where those pictures were taken. But this is the campus, and there's a big mall up the middle. And if you zoom in on that spot, this is where our building is. We've got 3 buildings. They comprise the College of Optical Sciences. This one's actually the biggest because it goes deep underground, and it's got a very tall optical test tower for measuring the properties of humongous mirrors. That our small optics shop is in that building. That makes 12-foot diameter stuff. And then our big optics shop is under the football stadium, and there we make 30-foot diameter optics, which get pieced together to make 80-foot diameter telescopes. So it's kind of a lot of classical optics, which is outside of my domain, which is why I'm having fun there, because I get to learn and reinvent yourself. And I think we should all reinvent ourselves every time we have an opportunity to do that. The profile of the college, we've got about 30 tenure track faculty, and then about another 30 research faculty, so together about 60 faculty, a lot of adjunct faculty, and then joint appointments and spanning a whole bunch of departments that are really heavily involved in our research program. And our student profile is mostly PhDs, about 200 PhDs. This is current numbers, I guess only about 100 masters right now, 100 or so with certificate students. And then recently, in about mid-2000s, we started having an undergraduate program, and that's when we became a college rather than a center. Over the years, 2,400 students. This is already outdated, which puts us out at the same level as the University of Rochester in terms of graduating optics students, but they've been at it for more than twice as long. So we're at a much steeper slope, and we currently have the largest optics and photonics research program in the country. A lot of very esteemed faculty recognized with national academies or even Nobel Prize winners, and several of our faculty have recently been presidents of the SPIE or the Optical Society, so very involved. And our research profile is pretty significant. We've got about $33 million a year in research expenditures in this College of Optics, and our groups these are not departments, but they're kind of like departments. We've got a group doing very core optical physics, and then imaging science that's heavily involved with biomedical imaging, image processing that might be used for NMR or things like that. And then these two are really the kind of core of our activity. The optical engineering and design is what really distinguishes us from being an applied physics department that you might see, or work that goes on in EE departments around the country. This is where we really do these, actually fabricate and make and engineer big optical systems and small optical systems. And then we have a photonics and optoelectronics and communications group. In fact, Arizona wasn't a big player in the development of optical fiber communications, but they've invested heavily before I got there. And now we lead the only engineering research center in the US in optical fiber communications. So very quickly came up to speed and trying to contribute strongly in that area. So that's just a little bit about our university. The actual talk I'm going to give now, I'll switch gears, and I want to talk about photonic integration. I'll give you a little bit about the history of PICs, as Mike pointed out, Photonic Integrated Circuits, and then talk about the progress in areas such as Silicon Photonics, which is one of the new areas that you're also involved in heavily here at the University of Delaware. And then I want to talk about some shifts and what's making things happen in the marketplace and what are the opportunities in the future. This talk will be a little bit more about why rather than the what. I like to give talks where I reflect on what's making things happen, why do companies invest in what they want to do, what makes things useful, and so forth. So the talk will be laced with that kind of thing. And I'll start out with this first, but before I do, I'm going to give you the walkaway. At the end of this talk, if you don't remember anything else, this is some of the things I'd like you to think about, that these PICs are very powerful, and they give you benefits in what we call swap, size, weight, and power, but also reliability. And Silicon Photonics brings with it a very powerful opportunity for more intimacy with electronics, and that's why it's so important. And one of the little benefits of that is that we can kind of get away from transmission lines and terminations and wasting a lot of power. And that there's going to be a set of emerging market applications that I think will drive this photonics in a new way, which is going to be very exciting for all of us in the field. And unfortunately, it's not easy. And so to realize that opportunity, we've got a lot of challenges as a community that we haven't yet geared up to do. I was excited today to learn that some of you, some of the faculty here understand these issues and are mobilizing to work on them. So I think you're already in it, and you're ready to be a participant in this stuff. So let me turn the clock back. Here we are in 1969, and a very prophetic paper was published by Stu Miller, who was the director at Bell Labs at the time. And if you look at the words, what he's talking about is a proposal for miniature laser beam circuitry on a chip. And the key point is that we're going to use photolithographic techniques that have been the mainstay for the electronics industry to do optics. So you can construct complex circuit patterns, miniature forms of lasers, modulators, and hybrids. So, you know, he saw the whole thing. He kind of laid it out there as a vision way ahead of the physical capability of actually doing this stuff. And if we look at what kinds of things people have in mind for a photonic integrated circuit, this is a cartoon I borrowed from one of my colleagues from Bell Labs, Steve Karatke, but it shows what we have in mind. So as Mike's pointed out, this is guided wave optics. We have inputs here from fibers, perhaps, that go into splitters, switches. You have detectors, tunable lasers, modulators, and so forth, filters. So all the things you might do to process, generate signals, detect them, modulate them, and process things, and so forth, you were going to try to do on a chip. And the point here is that you were going to monolithically integrate and interconnect all these things somehow on a common substrate. And so that was the vision. In order for this to become real, people had to have a really good reason for wanting to do it. And the reality was, for years and years and years, optical fiber communication consisted of a circuit that drove an LED and a single component, and it put it on a fiber, and at the other end you had a photodetector or a laser instead of an LED. And so there wasn't really much opportunity for integrating anything. But once you started to do that, and a very common example in the early days was encoding information at higher rates while keeping waveform fidelity on an optical signal, then you could do by directly modulating. So when you started out, you would just turn a laser on and off with the current. Unfortunately, when you do that, the spectrum jiggles around and it can't go as fast as you'd want to go. So people realized that they would do better by having a CW laser and a modulator. And unfortunately, each one of these comes in its own separate gold box. And you have very expensive robotics, expensive materials to keep the alignment precise. And so these packages actually dominate the cost of these components, and maybe 80% of it. But they're larger. You lose power every time you couple in and out of a fiber. You might have another dB or more of loss. And so there's all kinds of reasons why it's kind of foolish. If you know you're going to build these together, why not have one box and somehow find a way to integrate these components together? So in order for people to make these investments and realize all these benefits that they could get by integration, you needed some kind of a stable configuration. In this case, a laser and a modulator. It's incredibly simple, but you knew you were going to need zillions of these things. So it was worth investing in the difficult materials technology to be able to integrate lasers and modulators onto the same chip. It's not an easy thing to do. They're very different devices. They have different layer requirements, different doping, et cetera. So you have to find a way to do that. And you're only going to invest in that as a company if you know that people are going to want this, not just today. They're going to want it 5 years from now, and they're going to want 1 million of these things. Then you'll say, all right, I'll hunker down and I'll make that investment, and I'll get all the benefits of size, weight, and power that I predict here. And that was the case. So here's some examples of what I'll call first generation photonic integrated circuits. One of them is this laser modulator that I just talked about. And these are the examples. I'll be parochial in the ones I show because they're ones that I either contributed to or were near and dear to my heart when we used to work at Bell Labs or Lucent Technologies. So here's an example of a DFB laser with a integrated electroabsorption modulator, which is a material where you put on an electric field and the band gap changes and it absorbs the light or doesn't absorb the light depending on the bias here. And those were put into transceivers and sold in very, very large volumes. The year I left, or before we left, I left Bell Labs or Lucent Technologies, we were getting close, somewhere well in excess of $500 million, close to $1 billion a year, just selling these things, those little chips and modules. And people also made tunable lasers. So here's an example from JDS Uniphase, a company started by Larry Cauldron, where it's a widely tunable laser. And you can see this chip here with the bond wires going to the different sections. So by biasing these sections at different levels, you could control the wavelength of this laser sweep or choose the wavelength that you might need for a wavelength division multiplex communication system. There were other ways to make such a tunable laser. Here's one from a company called Aclaro, and you can see the chip there again. Here's an array of DFB lasers, which is another way of tuning. You just pick the laser you want that's at the right color, and then change the temperature of the chip to locally scan it. And when you want to go too far, you just switch to the next laser and scan that one. So there's lots of ways to make tunable lasers, and those were examples where the market really had a demand. People needed these things, and they were willing to pay quite a premium for these very simple photonic integrated circuits. So the natural question was, wow, is this going to be like VLSI? Is it going to be like electronic integration? Are we going to see the number of photonic components on a chip go up dramatically year after year after year to the point where we have billion transistors on a chip and optics? And I want you to remember, in the case of functionality, if you tried to make your cell phone today out of discrete electronics and transistors, it would be, well, first of all, it wouldn't work. It wouldn't be reliable enough. It would be the size of a pretty good sized building, and it would be ridiculously expensive to test and power, and frankly, you would never be able to do it. So in the case of electronics, integration is completely enabling, and you say, oh, the same thing is true for photonics. And I think the answer is be careful with that analogy, because if we think about electronics, what really made that scaling work was that these were massively repetitive elements of logic gates that enabled people to do digital logic on a larger and larger scale. What that meant is you could support more and more sophistication in your software and the functionality. So it's really software that led people to make the investments that kept Moore's law, keeps Moore's law today, just going on and on and on. And in the case of photonics, we might say what I said in the beginning. It's about injecting light onto a fiber and detecting it on the other end. Where's the scaling coming from? So at some point, you'd say it's not really the same. But fortunately, I think there's some hope, and it's because today, the applications you do on your cell phone are really in the cloud. And so just like the microprocessor that powers the software that you all love on your tablet or whatever it is, when you do things on the cloud, the infrastructure, communication infrastructure, and in particular inside a data center, is now the processing engine that's enabling this application to work. So in that sense, photonics is now a critical part of the fabric that's part of the economy of delivering what you want to do as a consumer. So I think it's got some hope that we'll see more investment going in, and I'll get a little more explicit about this later on. So let's go back to these stable configurations. So what was another example? In order to get more and more information on the fiber, we went through the stage of wavelength division multiplexing, which is another way of saying, I'm just going to have a whole bunch of independent colors and signals of different lasers, and they all transparently go on the fiber, and they don't talk to each other. They don't even know each other are there until nonlinearities creep in. But in order to inject all those different colors on the fiber, we need a whole bunch of lasers. We need to combine them together with some wavelength selective element. And on the receiving end, we have to do the same thing. We have to peel them all apart again. Well, if every fiber transmission system out there is going to use this multicolor scheme, this now becomes an incredibly repetitive thing. You do it over and over and over again. And if each one of these things is a separately packaged box, it's expensive and it's stupid. You know, why would you do that? Why don't we put all this on a chip? Well, the first company that committed to actually do that was founded by colleagues of ours that we all know well. In fact, Dave Welch, one of the founders, is an alum, an undergraduate here at University of Delaware. And they made the commitment to take all these components here, all these lasers and modulators and wavelength blockers and et cetera, and same thing on the receive side, and put them onto a single chip. So here's an example of what they've done. This is a single piece of indium phosphide with all that stuff on it. And it's only a few millimeters on a side, maybe 5 millimeters on a side. So this is an example of a more modern second generation photonic integrated circuit. And it's really the beginning of kind of ramping up the curve. We're trying to get more and more components on a chip. And these are real. They're out there deployed in the network today. They carry humongous volumes of traffic, and they've proven to be incredibly reliable. I don't want to be here on a soapbox like I'm an advertisement for Infinera, but they will tell you that they've had no field failures of these devices since they started deploying them 5 years ago. So they're out there, and the reliability is now at the point where they're better than what was required for the best undersea system, which is like space qualification. So very, very high reliability, and that's one of the things you get with integration, just like in electronics. If the transistors were the same reliability as discretes, you would never be able to make billion transistor integrated circuits. So this stuff is real. Another area where it's creeping in today is in Coherent. Light waves transmission until Coherent came was really turning the amplitude of a light signal on and off. Very different than what we do in modern radio, where you encode information on the phase of a carrier, and you change the phase to have a bit and maybe multiple different phases. You can have anywhere up to 128 or more different amplitude and phase configurations in a signal. In Coherent, you're going to try to do the same thing. You're going to treat the optical field as a coherent waveform, as a sine wave, and you can change the phase to encode information on it or change the intensity. But in order to do that, we have to get local oscillators, heterodyne receivers, and so forth. And we tried to do this years ago. In fact, it worked quite nicely. This is from the late 1980s. We made single chip photonic integrated circuits. This is one that I made with a good colleague of mine, Uzi Koren, which had a tunable laser and a combiner and detectors on it. So the incoming signal would come here and it would beat with the local oscillator tuned to a particular offset. And this really worked, and we could transmit data. It was way ahead of its time. My director at the time, a very famous fellow named Hervé Kogelnick, said, "Why are you working on this? You should be doing WDM." And I said, "Well, this is cool. You know, we thought this was more fun." We did WDM too, but he was right that this sat on the shelf for a very, very long time. But now it's back. And so Infinera, again, is making coherent receiver photonic integrated circuits. And this shows an architecture of just one channel. They'll have 10 channels, for example, but they have, on one channel, they'll have a local oscillator tuned to receive a particular wavelength. And the incoming signals here in two different polarizations will come in. One polarization goes this way, the other one goes this way, and it comes out, and it beats with this local oscillator and goes into paired detectors where you can measure these constellation diagrams. So this is QPSK modulation, where there's 4 different phases of the optical signal, and you can see this is a very, very clean data signal here, in this case operating at 25 gigabaud for a very high data rate, aggregate data rate here with 10 channels. So this is real, and I find it kind of rewarding because when we did our chip, this one back in 1989, 1990, people said, you can't put a local oscillator on the same chip. It'll have reflections and it destabilizes the laser. That's stupid. We found that it worked, and we kind of knew why it worked, but these guys are doing it today, and they find that it works very well. This is now commercialized stuff. It's real. And this shows the transmission side. So similarly, on the transmit side, you have to do that phase encoding. This shows the DFB single frequency lasers that go into these cascaded Mach-Zehnder modulators, and it allows you to generate one of those 4 different phases in each bit period. And this shows the actual layout of what that looks like, just this active laser portion on a chip. And you can see the density of integration there is extremely high. So photonic integration is real. It's out there in the field, and people are making fairly sophisticated things. So I would say at this point, photonic integration is now a little different. It's no longer just about making lower size, weight, and power of a known, proven application of photonics, and that's done with discretes. It's now really fundamentally enabling, because if you tried to make something like this or something like this with discrete components, it's frankly a nightmare. You would not get it to work very stably. These modulators don't work very well if you try to do that with discrete elements. So you have to keep the phase relationships so precisely and so forth. So it's switched from being just size, weight, and power to being a truly enabling technology, which is an important change. I think now there's architectures being pursued that you wouldn't ever even try to do with discrete components. So let me switch gears now, and I want to talk about the new guy on the block, which is Silicon Photonics, and talk about some of the inherent benefits and things we get with Silicon Photonics. So the first question you should ask is, why would I do Silicon Photonics? I can't make a silicon laser. Silicon isn't a good photodetector at these telecommunication wavelengths. It's maybe not even that great a modulator. Why am I going to try to do this? And in fact, when it first came out, I'll get to this in a second, but most of us in the field were very, very skeptical that there was anything worth pursuing here. But the reason you're doing it is very different, and it has to do, on one hand, with the technology, just the maturity of the technology. There's no other technology in the history of mankind that's had $40 billion a year of investment pumped in year after year after year to keep the industry on Moore's law. So what that led to is process technologies which could give you the kind of reliability that 2 billion transistors on a chip and have the yield high enough so that you can sell that thing for tens of dollars or something. It's crazy. You can't do that in the world of 3.5s. We can't make features, this is already very outdated. We can't make things where it's only tens of nanometers in dimension with very high reliability. We don't have 10 layers of metallization and all the process sophistication in these compound semiconductors. So the question is, and all the CAD tools with the predictability of a process where you can make a tape out and have a development team that finishes the project, gets a tape out, and they move on to the next thing, and nobody has even made anything. And it's because it's so reliable, they know it's going to work when the tape out works. Not the world of 3.5 photonics. So the question is, can I do this? Can I borrow this technology? And if I could do photonics with it, it would be so reproducible and potentially so cheap that even if it's a crummy optical material, maybe I can do something useful. So that was the premise, and it led to a whole bunch of research, a lot of DARPA funding, a lot of great work around the country to answer that question. And this just shows some of the results from, in this case, from IBM, which shows an example of a cascaded ring filter where you have light going in. And because of the high index contrast between silicon and air, or silicon and silicon dioxide, it's 3.5 index to 1, or 1.5 for oxide. That means you can make really, really tight waveguides, and you can bend very, very sharply around corners. So here's an example of very small ring resonators that are coupled to each other. And as I pointed out, the reproducibility of these processes is such that it's quite remarkable. You can make something like this and model it, what the filter characteristics are going to look like with different numbers of rings, and then you make it, and by golly, it actually looks like what you wanted. If you worked in 3.5s, you know it doesn't work that way. So it's a nice technology for its reproducibility. In order to make it active, I mentioned when this came out in the 1980s, one of the pioneers was a fellow named Richard Soroff, and a number of the faculty here know Richard well and work with him. He came out and said, let's do photonics and silicon. And most of us working in 3.5 said, what are you smoking? But he persevered, and he did some very good fundamental work to measure index changes as a function of plasma carrier densities. So you get free carriers in these things, minority carriers, and it changes the index of refraction. And you can make modulators by forward biasing a junction. Unfortunately, when you do that, you get a single pole filter response with this lifetime tau, typically a nanosecond or something. So these modulators based on this are slow. They're only 100 megahertz or something like that. But if you do reverse bias, and you do depletion or accumulation, then there's no such effect. It's a majority carrier device. You don't need to wait for anything to recombine. You can just do a depletion there and pull carriers away from a junction or load them up on a capacitor, and I'll give some examples of that. It's really limited only by RC parasitics or perhaps dielectric relaxation times, and they're very fast. So right away, companies who had invested in this space, one of the early ones was a company called Luxtera, who's still around today, and this shows their modulator concept. They have a silicon on insulator. This is a commercial wafer that you can buy, and they would make this is an end-on view of a waveguide that's a ridge waveguide, so an optical mode sits here, and by depleting the free carriers in and out of that mode, you can change the index of refraction, and if you then put that in one arm of an interferometric device, you can make a modulator, a Mach-Zehnder modulator out of that, and readily get bandwidths up in the 20 gigahertz range. So very, very high performance, and this is way back in 2006. A company that I was closely affiliated with was called Lightwire, and they have a different concept. It was an oxide gate, and so this was much closer to a CMOS product as it is. It's the same gate as a transistor. So this is polysilicon on top, single crystal here, and just by putting charge on that capacitor, just by charging it up, you change the index of refraction of an optical mode that sits on this waveguide, and able to get very high speed modulation, very good extinction ratios, in particular at drive voltages that are just like a CMOS. So it looks like another gate to a CMOS circuit. And I'll come back to that in a second. So here's a bunch of math. I'm not going to go through it all, but I want to give you a flavor for what this means. One time when I was bored, I wanted to figure out what the scaling limits were for this technology. And so here's a picture of a modulator, as I showed this depletion modulator. And if you remember your p-n junction physics, you can figure out the length of the n-type depletion layer and the p-type layer. And if you want to figure out the change in the index of refraction, you just have to figure out what's the index change of this region, what's the index change in that region, and how much are they confined in this optical mode. And this shows that formula. Total index change is this. And you can estimate what these confinement factors are. They're roughly the width of that thing divided by the width of the optical mode. And if you now require that you get a pi on 2 phase shift to get a Mach-Zehnder modulator out of this thing, you can figure out how long this device has to be. And the depletion region is governed by the maximum field in the middle of this thing. The electric field looks like that. And you find that the length of the device divided by the width of the mode is some number. And there's no design parameters in there. It's kind of neat. The only thing that matters is the maximum field strength. So that is a design parameter. If I have a low doping, that field strength won't be that high. If I have a high field strength, the doping will be, that maximum field will get close to breakdown at some point. And if I want to figure out, in fact, what's the shortest device I can have, I can see already I'd like to have a very tight mode. And all that means is that I'm concentrating the light right on where that index change occurs. That's always a good thing to do. But it also depends on this maximum field strength. So if I design that to be at dielectric breakdown in silicon, I find that the length to the width is a number of about 3,000. And what that tells me is the smallest mode I can make is about half a micron. And these are going to be millimeter, multi-millimeter devices. It's not like a nanometer scale transistor. So these are big, big devices. That's not great news. But it's still small enough where you can put them on an integrated chip. So it still might be interesting. And in fact, this turns out to be the case. So there's no real rocket science in there. It's just simple p-n junction physics. If we look at that alternate design that I was looking at there, the formula ends up being identical. It's the same physics instead of a p-n junction. The only difference here is that the maximum field strength is that of SiO2, and the dielectric constant is that of SiO2 too. So that's bad because that's a smaller number. That makes this bigger. But this maximum field strength is really much higher in an oxide than it is in silicon. So if I design these things properly, these devices can be about 10 times shorter than the p-n junction reverse bias ones, which is a very good thing because it turns out when they're very short, I can treat this thing, the transit time across it is short enough where I can treat it like a lumped element. I don't have to have a phased match transmission line to drive this thing. So I can treat it like a lumped element device even at these speeds of tens or 20 or 30 gigabits per second. And that means I don't need a transmission line and a termination. And I treat this just like another gate. That means I don't need 50 ohms. So that's another math slide. I'm not going to expect you to follow it, but you can go through the same physics to ask how much energy does it take to switch a bit. And it really is about how much charge do I need to put on and off that capacitor, or how much do I need to extract. So if I go through that calculation, in order to get that pi on 2 phase shift, I find out the charge is given by this number. And the only thing that matters is the area of the optical mode. That's the only variable. So I want to make the cross-sectional area of that optical mode really small. And that'll mean it'll be a low energy device. And I want to figure out how much energy. Well, if I know the charge and I know the voltage, then I know the energy. What's the voltage? Well, the voltage, this thing's going to be driven by a transistor somewhere. And so the voltage is going to be the voltage of a transistor. I could have something where I scale it down and have a divider circuit, but at some point, that current that I'm delivering, the charge is still coming off that transistor. So unless I had a transformer or something like that, I can't do that. So the voltage I put in here is the CMOS gate voltage, and it turns out it's the only thing that matters then is the cross-sectional area of the mode. So if I stick in a number for a typical mode in the Silicon Photonics, it might be 0.2 of a micron by 0.5 micron, I found out that I get about 2 picojoules per bit. And that means at 10 gigabits per second, this is going to consume about 20 milliwatts. That's pretty much exactly what you measure in these things. It's more like 30 milliwatts because you can't operate literally at breakdown and so forth. And, but it's a very good judge of what you're going to do with this thing. It's 2 picojoules per bit, which isn't where people need to be for some applications. So I'll address that in a second. But before I do, I want to think about this transit time thing again and remind you that if the microprocessor inside this laptop had a 50 ohm termination on each gate inside the integrated circuit, it would vaporize in about a microsecond. And it would take a 50 megawatt nuclear reactor to run it. So the question is, why in photonics do we run around with transmission lines and terminations and dump all this power into heat? And the answer is we shouldn't. And one of the potentials of silicon photonics is that I can get my electronics and my photonics to be so intimate that I don't need to worry about transmission lines. I can just directly power devices right off of logic gates and have things work that way. And that might end up being a very, very powerful thing. So again, in silicon photonics, maybe we can eliminate transmission lines and get rid of this termination thing. I want to briefly talk about other ways to get lower energy. So one of them is, can I do better than just making an interferometric modulator? And so if I change the index of refraction, is there some way I can do a better job? And one answer is, yeah, I can use a resonator. And all that means is that I'm going to change the index, but I'm going to reuse that light path over and over and over again. By circulating light inside a resonator, I can accumulate a larger phase shift effectively and get more bang for my buck. The way you do that is you make a resonator which has a resonance, a transmission resonance, for example, and I put a laser beam right on that transmission resonance, and then if I change the index of the material in the resonator, I'll shift it over, and I'm no longer transmitting. So I can make a really high Q resonator, and then I only have to move it a little bit, and I can get modulation with a very, very small index change. So that's potentially exciting. The limit of that is that if I make that resonator too high a Q, and then I move it, it takes a while for it to ring down, because it's a high Q resonator. It stores energy, and it only dissipates the energy slowly. So the width of that optical resonance will determine my bandwidth of this device. So the limit is I design that bandwidth right at the same bandwidth of the signal I want to transmit. And if I do that matching here, the energy per bit ends up being this, same kind of formula. And now the volume of the mode comes in instead of the area of the mode. And if I run through the numbers of a typical device I could get where the bandwidth or the Q of the resonator is matched to the bandwidth of the signal, I find out that I can get below a femtojoule per bit, I would predict. And experimentally, people are pretty close to that. So it turns out to be true. The best in class results were from Mike Watts when he was at Lincoln Labs. Now he's a professor at MIT, and he was getting down into the handful of femtojoules per bit. So it's pretty close to this thing that you'd predict here. And this is how they made it. You can see all the pillars here for getting the metal signals into these silicon microdisc resonators. Try doing that in 3/5. You know, the process technology to be able to produce that is quite remarkable. So again, being able to make things like this, very high Q resonators where you contact different layers and get all the metallization in there, that's what you get with silicon photonics. And it's also been done, this is an example from Koch, where not only do they make these ring resonator modulators, but they put heaters on them and they elevate it above the surface so the heat doesn't dissipate into the substrate, so that as the laser drifts in wavelengths, you can actually tune this thing so it stays on resonance to address that problem. And that ends up consuming a fair amount of power, but even with that tuning, it's still in the range of 100 femtojoules per bit. So it's pretty impressive technology. So this is the last math slide. So one of the questions is how low energy could I go? And one of the things you could do is, rather than use the plasma effect, which is just putting free carriers that are polarizable in an electric field, they move. What if I put a resonant atomic system in there, like a quantum dot or something like that, that had a resonant bound transition that I was going to make? So that'll change the index a lot more. And if I put that in effect and I do resonant electronics and resonant optics, I could get the energy really low. And this is the formula you get when you do that. And if you stick in the math, again, the volume of the mode is there. The bandwidth shows up twice because I need to match the electronic bandwidth to the optical system. But what you find out is that one electron is enough to turn on and off a 10 gigabit signal. You can actually make a system where a single electron in or out of the system is enough to turn the light on and off with full extinction. Now, that's a kind of a pie in the sky vision that you could do that, but it gives you a target to shoot for. And what it also says is that the plasma effect may not be the best thing to jump on. Maybe we should be using quantum dots. Maybe we should be using other index changing mechanisms. And here's an example of doing that. This is a on-off modulator, but it uses the electroabsorption effect, the Franz-Keldysh effect in germanium. And this is from a team from MIT and I think BAE Systems, where they fabricated this device. And here's the waveguide. And by putting an electric field across the germanium, you change the band gap and you get absorption or no absorption. And this device ended up with a number of 50 femtojoules per bit just in a straight path modulator, not using the resonance. So this is an example, a different index mechanism. If I now added a resonant structure to this, I would get down way below a femtojoule per bit. And I'm surprised that nobody's done that yet. If you're out there, you should be the first one to do it, because it's pretty straightforward to combine these effects. And in this case, you could make a resonant transmitting modulator that was quenched when you turned on the absorption, for example. And that would be an easy thing to do, and I guarantee you'd get down into the attijoules per bit kind of regime. I'm still waiting to see that in the literature. So that was modulators. What about detectors? Well, it turns out germanium is already in the silicon fabs, so we can make germanium detectors. This shows an example from Koch, where they have a large layer of germanium in a waveguide configuration. And I'm not going to dwell on it, but just to show you that the bandwidths are very, very high, up in the 30 gigahertz range, and the responsivity is outstanding. So these are good photodetectors. In fact, in the silicon material system, people have found that they can make better photodetectors than they could in 3.5s. So 3.5 is the bread and butter. Indium phosphide, indium gallium arsenide is the bread and butter of this field. But in the case of avalanche photodiodes, because silicon has an amazing multiplication characteristic, very low noise avalanche multiplication, you can make a lower noise, higher gain photodetector than you can in 3.5s. And so teams from Intel and UCSB and Joe Campbell at the University of Virginia were able to demonstrate both surface normal and waveguide APDs that have gain bandwidth products that exceed anything you can do in the world of just plain indium phosphide or indium gallium arsenide. So detectors are a pretty good story. So what's the weakness? Well, the weak point is sources. So today, people are not really trying to design real products or anything with sources on the chip. Instead, they couple onto the chip. So you have an outside laser. I have all these waveguides and modulation and filters and detectors and so forth on silicon, and I couple light onto the silicon chip from an external laser. And one way of doing that is with the surface normal grating. If I have a waveguide with a grating in it this way and I come in with light, I can couple the light from the air into the waveguide, and I can do that pretty efficiently. This shows an example of the bandwidth over the optical domain of coupling from Luxtera of coupling into a waveguide. And you can see the loss is in the range of 1 dB over a pretty wide window. So it works quite well. And that's important just to get the light into a chip, but also people are now working with multi-core fibers, and they want to be able to detect light in very closely spaced patterns. So I need super compact detectors. And one way to do that is to make the launch pads very tightly spaced to match a fiber, and then have the detectors be somewhere else on the chip. So this kind of technology is kind of tailor-made for this new research area of multi-mode transmission in fibers for very high data rates. Other ways of getting light into a fiber are shown here. This is a collaborative project that Coherent did, I think with SciOptics. And you can see lasers here that are just surface mounted into waveguides in silicon. So here's a waveguide array and a laser array. You can do folding mirrors for doing photodetector hybridization and so forth. So this is another option. This is some work from the company Lightwire that was acquired by Cisco, and it shows a trough for a fiber and a waveguide where the end of the waveguide is tapered down on a nanoscale to expand the optical mode to try to go from this fractional micron optical mode to the larger optical mode of a fiber, and that works quite nicely. And this shows the fact that it doesn't have any significant wavelength dependence, unlike the gratings. So this is a more conventional approach, perhaps. Now, the most provocative approach that's out there right now is to try to do clever techniques where you bond compound semiconductor functionality onto the silicon. And this is an example where it shows a silicon waveguide from John Bauer's group at Santa Barbara. So a silicon waveguide, and then the 3,5 material is put on top of that intimately using van der Waals bonding. And you end up putting contacts on there, but you don't have to do any sophisticated lithography on the 3,5 material. You just put it on there and roughly align it, because the waveguide is really defined by this silicon underneath. So it's a hybrid device where the light is propagating mostly in the silicon, but part of it is up there in the 3,5 material, and it gets gain, and you can make pretty darn good lasers using this technology. This was very early result they had. You can see more than 5 years ago. They've progressed quite a bit since then. Other groups around the world are trying similar approaches. This shows a ring resonator with a layer of 3,5 and then an optical bus that's in the silicon underneath where the light couples from the ring resonator into this optical bus that goes underneath there. So a very small cavity, very low thresholds, but also very low powers. This is in microwatts, as opposed to 25 milliwatts in this case. So this group from UCSB has spun out a company called Arion, and they've worked with Intel to make a demonstration of very high bit rate wavelength multiplex transmitters where there's tunable lasers, 4 tunable lasers with modulators. So this is the 3,5 bonded on the silicon. These modulators are in silicon. This multiplexer is in silicon. And this is all a hybrid integrated chip. And it worked quite nicely, 50 gigabits per second. They're also doing things like switchable delay lines where they have different delays. And by turning on and off a semiconductor optical amplifier, you enable a transmission path or you turn it off. And you can make switch delay lines. They've also made these coherent receivers using this technology where the detectors are bonded indium gallium arsenide, for example. So you get indium gallium arsenide detectors on a silicon photonic chip. So it's an area that's being pursued aggressively by this company. People have also tried trying to make lasers directly in silicon. I was part of a MURI that led by MIT, and they were championing the concept of germanium being a lasing material. It's an indirect material, so normally it would not lase. But if you strain it just from the thermal growth up at 900 degrees, and then you cool it down to room temperature, you end up getting tensile strained germanium, and that improves the band gap offset a little bit. But then if you dope it very heavily, you can get this L valley filled up so that when we put in electrons, some of them end up then in this gamma valley, which is a direct transition. And lo and behold, you can make a laser that way. Here, this shows their more recent result with an electrically pumped laser. You can see the threshold here and the very, very high doping levels. You need to get up in the 10 to the 20th doping range in order for these things to work. So it's provocative. It's way too early to say if this is going to be have commercial impact, but it's interesting because all these materials are in the CMOS fabs already. So, is this all just fun and games, or is there something real that we're going to do with this technology? And the answer is, near term, there's some things that people are working on, but I think the big event has yet to happen. And let me elaborate on that. This shows an example of a coherent receiver done in Silicon Photonics in a collaboration between Bell Labs and IME over in Singapore. I'm not going to dwell on it, but it's in the mainstream of high capacity, long distance fiber communication. So people are thinking, well, maybe Silicon Photonics has an application there. Maybe, maybe not. You can do that other ways. As I showed you, Infinera has these chips all in indium phosphide. But if we look at the internet traffic, it just continues to go crazy. And if you look at what's really driving internet traffic now, it's all about video. And where is this crunch happening? It's all about what's going on inside data centers. So if we look at the traffic on the internet, what you see is that the dominant growth here is what we call cloud computing or cloud traffic. And it's all about the data centers. And here's a picture of a data center from a guy named Don Lee. It's not a Facebook data center. He's very quick to point that out. He's from Facebook. But it shows what these things look like. And lots and lots of optical fiber connecting servers together. And it's kind of a crazy scenario. Lots of power consumed. And if we look at high performance computing, this is a picture from IBM of one of their earlier supercomputers. And you can see all the fiber bundles here. And when you look at this and you look at this, you start to wonder, is this stuff really scalable? Is it really going to happen? Well, Silicon Photonics may have a play here. And one of the areas where, in fact, the only area where there's products for Silicon Photonics today is in trying to address these data center kind of markets. And they're in things like active cables where you have transceivers, optical transceivers embedded in these ends, and they look like electrical cables. So the system doesn't know it's an electrical cable. You plug it in, it's the same interface that would allow you to go this far, but because it's converted into optics, you can go across the data center using, or at some reasonable distance using cables, or individual transceivers, for example, that might go 5 kilometers or something like that. So Silicon Photonics is already commercialized in these areas, but and they're continuing to advance that technology. This shows the work that's Luxtera has talked about most recently, which is extending the data rates now up to 100 gigabits per second. And they do that with 4 optical lanes, each one modulated at 28 gigabits per second. And you can see here's their chip, and it's got electrical control circuitry, digital logic stuff on the same chip as the optics. So they're able to do this all in the same layer and get even measure the eye diagrams right on the, do bit error rate test set right on the chip to verify and self-test that these work. So they're pursuing that, and another area that's being pursued, this is from the Lightwire guys, is to do multi-level, they call it pulse amplitude modulation, so PAM16, and they're making Mach-Zehnder modulators with sections on them, so you can digitally control how deep you want to modulate the signal and get eye diagrams that look like this. This is an early result. They've gotten much better results since then. So this is another way to get more information, in this case 4 bits, inside one time slot, depending on which of these levels you're going to go on. So that's of interest. But I think the big event is yet to happen. And this is where I want to shift gears in the remaining amount of time I've got and talk to you about the application within computers as a computer interconnect. And we had a talk at our Group 4 Photonics meeting and also at the Integrated Photonics meeting that I chaired. We were able to get Justin Ratner, the CTO of Intel, to come and give us a spiel. And he's a supercomputer guy. And he made the point that all this work on supercomputers isn't really going to push the industry hard enough. It's so specialized. And even though the volumes are pretty large for these supercomputers, the latest IBM computer has 1 million lasers in it, that it's not pushing things hard enough. And what you really need are consumer applications. And his view was, so this is a supercomputer guy telling you that you're barking up the wrong tree, that you really want to focus on real consumer volume applications, or things like servers CPU to disk, CPU to RAM, high definition 3D video, they're all coming, and they all require a lot of interconnect bandwidth. And this just shows a cartoon from a publication in Japan, which shows what we're talking about. So you might have a CPU that needs to talk to memory, and to do that, you're going to want very high data rates that are best handled by optics. And it poses a really interesting question. So this is where I mentioned in the beginning, I want to talk about the why, not so much the what. And that if we look at the applications for photonics and communications, it's all been about very long distances, going into the metro world, maybe into access and into your home or within the central office. And the distances, as time goes on, it penetrates to shorter and shorter distances. But what characterizes these applications those are things where we know photonics plays a key role. And by doing photonic integration, we can save size, weight, and power, and we can do a more cost-effective job at those applications where we know photonics is important. But if we look at electronics and these even shorter distances, we've got CPU to disk, backplane connections inside a data center. But ultimately, we're going to be doing chip-to-chip communications, as I showed in that last cartoon, maybe even on-chip, maybe even multi-core optical networking on a chip. And these are characterized by shorter and shorter distances. What's most important about this is the driver here. So if we look at an application like chip-to-chip, what we're talking about here is that photonic integration is going to enable the scaling of electronic functionality, not just communication links. So now optics plays a different role. We have this juggernaut in electronics that has $40 billion a year investment to keep it on track and keep you buying the latest iPhone, or keep you getting your iPad, or doing cloud computing, whatever you're going to do. The engine behind that, video games, the engine behind that is huge, and it's got a really, really deep market, a lot of revenue to support that. And if now suddenly optics becomes critical to support that revenue stream, it's a very, very different picture than communication links. It now plays a very key role in keeping a roadmap going of something that's so important to our economy. So I think, and this is like that early view graph I showed, as soon as optics and photonics becomes critical to keep this going, it can change everything. So here's a cartoon from IBM where they show an example of an optical network on a stacked chip. You might have a logic plane, a memory plane, and then a photonics plane, and we might connect different cores on a processor and eventually go off the chip. So Silicon Photonics is the most credible platform to allow this kind of intimacy. I can use the same manufacturing technology to make all these chips and even stack them up. Now, one of the challenges is that the whole community ends up showing little arrows on the output, which are I/O, and frankly, that's always been the problem with photonics. That's why we did integration in the first place, is because getting in and out of the outside world is a big problem. So one of the areas I think we need to focus on is this I/O problem. And in photonics, we need assembly tools that look like this. I mean, this is what we do in electronics. We've got wire bonds where the connection costs some minuscule fraction of a penny. We can't do that in photonics. So what we need is some kind of solution where we can get out of a chip stack where we might have let's look down here, for example. We might have a photonics chip and an I/O chip, and an electronic processing chip, and using technologies like through silicon vias, TSV technology, we can drill holes and we can connect these different layers. And if we get down to a circuit board, like a conventional circuit board that we have now, we have electronic traces on the board. But if we really want to do high-speed connection, maybe we can have this photonics chip, which could be a silicon photonics chip, and it could get us into a waveguide layer and get us over to the next chip. So we need to come up with a technology that looks something like one of these. And I don't think we know what the answer is. This shows a talk that I gave on behalf of my buddies at this company, Lightwire, that showed their vision back in 2009, and it was exactly what I just showed you. There was an electronic gate that sits on top, and then we would have a SOI silicon photonics chip, and some kind of, so here's the waveguide layer there, and there would be some way to get this from this chip onto a waveguide. And that's really the challenge, is how do I do that alignment? How do I get light off this sophisticated 3.5 chip silicon photonic chip with these minuscule high density waveguides, how do I get that off to go to another chip using some kind of a low cost technology? And I personally think that's where the huge opportunity is. It goes into hybrid assembly techniques. And I'm personally excited because the industry, again, it's like silicon photonics. The whole premise of that was, can I do photonics? Can I use this economic development that created VLSI silicon? Can I do photonics with it? And the answer turned out to be, yeah, I can make chips. Well, now the question is, can I use something else that's developed in that industry to get this very hard problem of getting from one thing to another? And I think the answer is going to be yes again. And it's because they've developed these stacking tools. So the VLSI industry is now stacking chips on top of each other inside your cell phones, depending on which brand you've got. This is a consumer high volume thing, and the precision that's required to get these plugs to align, initially it's not so fine. It might be 10 microns, something like that, 5 microns. But they already have a roadmap where they know it's going to get smaller and smaller. So they're developing very high throughput, very precise tools that allow them to take these chips, slap them on top of each other, and align things at the level of a micron. So now the question's the same as with the front end. Can I use those tool sets to do optical packaging? And I don't want to call it packaging because people who do packaging, they think they know what they're talking about. It's a gold box with, robots that align things into fibers. This has nothing to do with fibers. This has to do with getting from one chip stack to another. And the only requirement will be, forget everything you know about packaging. And the only thing is to use these tools. That's the starting point. Because they're going to continue to invest in those. They're going to get better and better and better. And if you're not riding that horse, you're riding the wrong horse. So this is my opinion, just an opinion piece. But if you can develop an assembly technology, an optical assembly stacking technology that takes advantage of these tools, you win the game. Because what you wind up with is a capability to have arbitrarily complex photonics. You've seen how dense the silicon photonics can be. And we can get light onto there, either from the outside or through bonded silicon, 3/5s on the silicon. But I can have very, very high density, very high functionality optics arbitrarily linked at any point I want on an integrated circuit to get into that, do some processing, come back up into the photonics, go back down again, go to another chip stack somewhere. So not just in this computer interconnect application, but now let's suppose you're a DoD designer of some signal processing circuit that today you're doing with electronics, and you've got your modulators and your lasers over here, and you're working on the next generation, and you look over and you see something that looks like this, where somebody's got electronics and optics all integrated together, and you'll realize that if you're not designing into that capability, you're going to be trying to sell buggy whips. So I think when this happens, and it will happen, it's going to change the world of optics and photonics in a really dramatic way. Almost anything you want to do in photonics will benefit from this. So the way I've been pitching this is that we've done chapter 1 in silicon photonics. We asked, can we use the front end? And the answer was yes. And now we're ready to do chapter 2, which is, can I steal the back end, the assembly technology to do photonics? And I think the answer is very likely to be yes, and those who invest in realizing that will benefit in applications ranging from defense to biomed, sensors, the whole 9 yards. Anything you want to do with optics and signal processing will benefit from this. So that's the end of my talk. I want to end on one note about disruptive technologies. And we all use that term, but most of us don't use it in the way that the original coiner of the term meant. And it was a fellow named Clayton Christensen, and he wrote a book quite a while back called The Innovator's Dilemma. And the use of the term disruptive technology was to describe the following phenomena: that markets are served at the high end by some super technology. This is the need, the requirement of that technology. And as time goes on, people address that market and they make it better and better and better. And at some point, it actually exceeds the performance that's required. But guess what? It's a competitive market. And if you're selling this and the other guy's selling this, people buy the higher performance, even though they don't really need it that badly, but they want the highest performance. What the disruptive technology is, there's a totally different market set that has a completely different low demand in terms of performance, and people invent a technology to address this market. And once in a while, those technologies have a steeper slope where they address this market, but at some point they cross over and they get good enough to address this high performance market. They may never be as good as the technology currently is serving that market, but they get to the point where somebody looks over and goes, wow, that's so much cheaper, and it's good enough, I can use it. So this is what a disruptive technology is. It's a dirtbag technology. It's something that was made for another application that comes out of nowhere and suddenly is good enough where your Ferrari, you're willing to trade it in for a Yugo. And my belief is that Silicon Photonics, in our current situation, the high end of the market is telecom, and Silicon Photonics is really all about interconnects. And so is it a disruptive technology today? I'd say no, it's not. But because of this potential for incredible functionality and integration with electronics that I think will happen, it will be tomorrow's disruptive technology. So once we develop these assembly solutions, I think this technology will become so important that it will start to encroach on these more traditional solutions in telecom to the point where it becomes the currency of the realm. It'll be the only way to do things. So does it mean silicon takes over the world? Yes and no. We need 3.5s. We need to integrate in 3.5. So there's still a lot of important work to be done in optimally integrating 3.5 functionality in silicon. There's a huge amount of work to be done to figure out these assembly tools and how do I really take advantage of the progress in the back-end manufacturing of silicon. So that's the end, and these are my walk-away messages. I hope I've conveyed that I'm excited about this. I think something really remarkable is going to happen. And as soon as I wrote that line, I kind of got a little corny on you, and I'll got to apologize for this. But I thought of this movie, 2010, with Roy Scheider. I don't know if any of you ever saw that movie, but there's this scene in it where Dave Borman comes back, you know, as from being absorbed into the alien being, and
you see, something's going to happen. What? What's going to happen? Something wonderful.
yeah, so thank you very much. That's the end of my talk.
Floor is open for questions.
Yes.
The silicon nodes are always compared to the optical nodes, and it always seems like optical is 293 or 130, and silicon said it was 15. Any comments on that? Because it seems to be a common misunderstanding.
Right. So the question is that the most up-to-date generation of silicon is now going down to 22 nanometers, I guess, something like that. And that's much smaller than what we need for these optical devices, which maybe are, you know, at the 90 nanometer node or something like that. But the benefits you get from getting smaller and smaller are not that high, and the cost per unit real estate of these high density nodes, you know, the latest generation fabs for silicon cost multiple billions of dollars for these lithography, for the whole process technology. And they're also on huge wafers, and nobody wants to waste any of that real estate on a big photonic device that might be, you know, 100 microns long or something like that. So what do? That really only becomes an issue when you decide you're going to do electronics and photonics in the same chip. And then you have no choice. You've got to do the electronics and waste the real estate for these large photonic components. Most people are moving away from that, and their concepts are now going to this stacking technology where you say, I'm going to process the silicon chip, and I'm not confined to the same technology that I use for the electronics. It's especially important in some cases because people are using silicon on insulator, and when you go to the latest generations of silicon on insulator for electronics, the layer of the oxide is so thin that you can't even support a waveguide in the silicon anymore, in the device layer. So it kind of pushes you into this regime where you say, I'm going to do photonics in a different technology node. And for people who are exploring the field, that's good news because they can use a depreciated fab that's, you know, doing 130 nanometers or something like that, and it's not so expensive. whether that means that the industry ultimately stably settles into fabs with different design rules or not, I don't really know. But I think the short answer is that most people are now envisioning that those are two separate chips.
Is there any advantage with the smaller geometries to making optical devices more precise, like a ring resonator that always, brings it the same frequency or something like that?
I would say maybe, but it turns out the variability comes not so much from the fab of the ring, but it's from the thickness of the device layer and things like that in SOI. So it's not obvious to me that just getting a better design rule necessarily gives you the precision you need. So I think I'm kind of a believer in the fact that you probably don't want to keep following the electronics all the way, because that's also going to get increasingly kooky as people feverishly still try to stay on Moore's law. So it'll get increasingly strange, I think, and maybe increasingly versatile too. So yes, Dennis.
Great talk, really enjoyed it. Thank you for coming to Delaware. I got a question along the lines of telecom, to a large extent, can be thought of just conveying information from one point to another, as can optical interconnects. I was wondering, do you see emerging application areas where optics can do things that electronics can't? Like, obviously, one near and dear to my heart is like high-frequency RF local oscillators. What about things like MIMO and other stuff like that? Do you see applications coming where optics actually stands alone as opposed to just augmenting electronics?
Yeah, I know the answer is yes. I'm from the College of Optical Sciences. So, yeah, I think, so some of it is exactly in the fields you said, the signal processing and so forth. Optics is for, that's what Mike did when I knew Mike first at Caltech. He was doing optical signal processing, very clever techniques that save a lot of power. Some of them are more analog-like techniques where you don't have to number crunch and turn everything into bits and then bang away at it with digital logic. The other thing I think is secure in the optical domain is anything related to imaging. Or if you recognize that imaging is an incredibly rich communication channel space, that light is really good at communicating and dealing with images and taking advantage of space. So, so once you go into things that are more like free space and imaging, I think there's a wonderful future in more pure optics. But I guess I still feel like that doesn't detract from this message. It means if I now say I can give you a focal plane array and not just connect up to a chip in a simple way, but allow you to connect up with logic and shoot light around, inside a wafer or something like that. There might be some very powerful things that come out of that. So I think this intimacy with electronics isn't necessarily just in guided wave. It's in all kinds of devices.
So. I mean, you had a lot of discussion about, you can always go to higher Q when you don't have large refractive index change capabilities. But at some point you run into a problem, and you did mention, using onboard heaters and things like that to temperature stabilize. But I mean, at some point I would think that temperature stabilization is going to be a limitation of how high a Q modulator you can use.
The first thing you run into actually isn't that. It's just the information bandwidth. So you can't use a Q that exceeds the bandwidth of the communication channel. So you already run into that very easily with modest Qs of 10,000 or something like that. So yeah, we can make chips, it's been demonstrated with Qs of 10 to the 8th or something like that, and they'll ring for a millisecond. You can literally watch them.
Even at 10,000, what degree of temperature stabilization is required? I mean, just because of the walk-up of the refractive index with temperature?
Well, silicon's about the same as 3.5, so it's like a angstrom per degree, something like that. So, and an angstrom is 12 gigahertz, so that's about a degree for 10 gigabits, something like that.
So 1 degree.
Yeah, so it's not a killer, but that's really hard when you're on a microprocessor that's one part of it's scrambling eggs and the other part of it's not that hot. So it's not a trivial problem, and some people, would say, therefore, I can't use rings, but I don't think that you can get to these femtojoule kind of numbers easily without grappling with the heater issues. But yeah, the other answer is maybe you get more and more clever, and once you throw a good challenge out there to the engineering community, people are smart and they come up with new materials, and maybe maybe we can do some temperature insensitive material that's been demonstrated. You can have a polymer cladding that cancels out the index change, and you get temperature insensitive materials. So I don't know what the answer is, but usually if it's not a physics barrier and it's a technology barrier, if the reward is big enough, people will only be limited by the physics barrier, not the technology.
So I have a question kind of connected to Dan's question. But if people find a reason or motivation to build a computational photonic chip, what that motivation will be? Will the motivation different from the motivation to build an integrated photonic communication chip, or are there simply no such motivation to do general purpose computation in photonic ways?
So I'm not sure if you're starting to inquire about applications in optical logic processing, so optical computing, areas like that. That's a subject that's been worked for many years, and I think it's kind of in waves. A lot of excitement 20 years ago, over-excitement, over-enthusiasm, and then it kind of relaxed back down again. I don't think that means it's dead. There's still funded programs where people envision some level of optical processing at very, very high data rates, for example, as the front end to a processing system, which then gets farmed out to slower electronic processes. And maybe with increased sophistication with electronics, there will be clever new architectures that you come up with that might change that equation completely. So I don't think the story's over, but I don't know of anything that's so compelling today that it's obvious that it's going to take over the world and change the way we do computing. It's kind of like the hope that we had on 10 years ago, 15 years ago. Smart pixels was the word of the day, and I think there are some things that were done and can be done there that were powerful. People do hyperspectral imaging where they want to have lots of wavelengths that are simultaneously imaged, and that requires some sophistication. I think anything where you get electronics and photonics to be fundamentally intimate because they're manufactured on the same line with the same tools, and so it's going to change a lot of things. People will start looking at different ways of doing things to take advantage of something that's really cheap and powerful. So where that goes, I really have no idea. But I think it's kind of like lighting a wildfire. And once you light it, you don't really know what's going to happen. But I think it's going to change a lot. In a positive way, not burning down the landscape.
Well, with that, I think let's thank Tom.